SwayamPrabha. Digital India. Educated India.
So, let us continue our discussion on precipitation hardened aluminum copper alloys. I have already discussed with you about the structure, free energy as well as the sequence of the phase transformation in the aluminum copper alloy. As you know, if I artificially age aluminum copper alloy, first phase which forms from the supersurface solution is basically GP zones, and then it followed by theta double prime, theta prime and finally theta. So, people have actually measured the hardness as a function of aging time to understand what actually happens. So, if I plot, hardness is nothing but an important mechanical property which characterizes strength. So, suppose if this is my strength of the initial supersurface solution, and as the aging time goes on, it has been found that hardness of the alloy goes on increases, reaches a maximum value and then decreases. So, this kind of curve, which is nothing but a hardness of the aged alloy at suppose 150 degree Celsius temperature schematically, is known as the aging curve. Hardness initially increases, reaches a maximum, then decreases. So, initial increase is basically because of the formation of the GP zones and theta prime, theta double prime. So, because they are coherent precipitates to the matrix, coherent in all along crystallographic directions, therefore, if a dislocation has to move through these to cause deformation in the phase in the alloy, it has to basically cross huge barrier because of the coherency nature of the precipitates. And once theta double prime starts transforming to theta prime and theta, the coherency is slowly getting lost between the precipitate and the matrix, and because of that the hardness decreases. Because once the coherency is lost, dislocation can easily cut the precipitates and move, but when it is coherent, dislocation has to use Orr-On's mechanism for it to cross over. So, because of that the hardness decreases here, hardness increases there. So, this is very important. So, therefore, in industrial alloys, if you want to make proper heat treatment of the industrial aluminum copper alloys, you must heat treat in such way that we form theta double prime more large numbers in the microstructure. So, the strength is very high, and that is what actually happened. Yield strength values of what I have shown you in the earlier slides basically correspond to the peak age sample, the sample which has the maximum value of hardness, and this is known as peak aging. Remember, this is artificial aging. Why? Because we are heating it to higher temperatures after quenching the sample. Now, how the transformation actually happens? It basically happens because of sequence of precipitations. Why the sequence of precipitations takes place? That I already discussed, that is mainly because of the activation energy barrier for the nucleation varying as you go from GP zones to theta. Schematically, this slide shows you that. If you see, this is delta G as a function of size, GP zones are a very small size, right, they are very, very small, and they are basically sheets of copper layers on the aluminum alpha phase. So, because of that the barrier is very low, because the matrix is coherent with the precipitates and strain is also low, because only few layers of copper, the barrier is very low, because delta G is nothing but minus delta G V plus delta G strain. As you know, this delta G V is basically comes from chemical free energy change, and delta G S is basically coming from strain. We want to have a more negative delta G V for the activation barrier to reduce, because activation barrier delta G star is nothing but 16 by 3 pi r pi gamma q divided by delta G v minus plus delta G s square. So, as you see here, the gamma has a strong role, because gamma q, gamma is the interfacial energy between the specific and the matrix. So, gamma for these GP zones is very low, because every matrix is, the specific is very completely coherent to the matrix. So, that is the ideal situation you can think about it. On the other hand, delta Gb minus is also high, and this value minus delta Gb plus delta Gs is high, because delta Gs is small, strain is very small in GP zones. Because of that, delta G star is low. Delta G star is the activation barrier for the nucleation. But as you go from GP zones to theta double prime, there will be a slight increase of the activation barrier, as you see here. There is a slight increase, but not much. Okay, basically size has increased, but the activation barrier has not changed drastically. It is very minute change. That is obvious, because again theta double prime is coherent. Only thing which could have changed, or which normally can change, is basically strain energy, which is little higher because of the presence of the copper atoms. More logically they are present, or more specifically they are present in the crystal. But on the other hand, if you look at theta theta prime, activation energy is high. Correct, that is very high, and slowly it is increasing, and so stepwise. Correct. So, if you have to add these and these to obtain this one, okay, although it is not shown schematically. So, finally total energy change is basically each of these together, this plus this plus this plus this, okay. So, that is what actually happens when the sequential transformation happens, and this is the reason why the sequential transformation happens, because the energy change happens in a sequential manner, not in one step. If it has to happen in one step, the energy barrier is very high. You see here alpha 0 going to alpha 4 plus theta. So, precipitation of theta and the activation barrier for nucleation is pretty high, and this is not desirable in a solid state phase transformation, because energetically they are very demanding, and because of that this direct transformation is never observed in these alloys. And again I am showing you total free energy versus time. If you see here, if it has to change G0 to G4, that is the total free energy change, but it happens in a slow manner. First it decreases this much forming GP zones, then it decreases this much to form theta double prime, then it decreases this much to form theta prime and theta. On the other hand, as it is shown here, total energy change is, if you want to change alpha to theta, alpha 0 to theta, is very high. Okay, so therefore system behaves in a logical manner. That is what I have been telling, that it transforms in a sequence from from alpha 0 to theta, and we can actually control that. We can stop our heat treatment here, then we will have only theta double prime in the microstructure, and some amount of GP zones will be present obviously. So, this is give us the best combination of the mechanical properties, hardness and the strength, hardness, strength, also ductility, because theta double prime and GP zones are completely coherent, so hardness will be high, and because of that these are very useful. Remember, all the plane bodies for the commercial aircrafts, they are actually aluminum copper alloys, in which these precipitations are directly used to create high strength. That is one part, and now I just want to go back and discuss with you some more things about these precipitations. As I said, GP zones actually can form in a very logical manner. We can actually generate these, using these data we can actually generate a time temperature curve, and let us do that. This is there actually on the phase diagram. First I will draw the phase diagram, and then I will draw the rest of the things to show you how things actually happens. So, let me just do it on the board. So, as you have seen, the phase diagram looks like this. This is 660 degrees Celsius because this is aluminum melting temperature, and this is weight percent copper. Okay, and we are not drawing it to show you that. As you have seen that actually this looks like, the phase diagram looks like little bit like this. So this is basically theta solvus. Basically there is eutectic reaction here, that's much higher, and there is, and this is theta actually. So ideally speaking this will be alpha plus theta. But our alloys will be all less than these values, so about 4.4%. So therefore this is theta, and theta double prime, so theta prime will be this one, the solvus line. You can clearly see that, and similarly we can actually draw solvus line for theta double prime and solvus line for the, this is a solvus. Okay, let me just draw it very carefully and show you. Why it is solvus? Because it shows you the solid solubility of copper as a function of time in the alpha phase. You see here it is decreasing continuously. So because these phases theta prime, theta double prime and GP zones, they are actually metastable. So we show them by dotted lines in the phase diagram. These are the solvers for that. So therefore if I have to draw the whole phase diagram, this, because this has shifted, so everything will shift. So that means this will shift like this. You see here, this line will shift like that. So similarly you can actually shift everything and do that. So this will also shift into this and become like that. So which normally not shown in the books. So let us not do that, but frankly speaking this is how it will look like. So these dotted lines tells you how the precipitation happens in the alloys. Now using this data we can actually make time temperature plot. This is temperature, this is log time, and this is known as basically TTT curve in the literature. That we will discuss much detail in case of steel, but here it is basically aging curve. Now how I am going to draw it, please look at carefully. First I will build on these things, this phase diagram. So I will just take the phase diagram directly from it. So this is my alpha, okay, and then one can draw it. It does not matter whether you keep it or not. And let me just then draw theta, this is theta prime, theta double prime, right, and then this is GP zone. Now if we simply drop a vertical line at about 4%, okay, copper. Remember this vertical line, although this axis is time, but we can actually transpose these things into here. So what I will do now? So obviously for the theta, this is a TTT curve, so it will look like a C-shaped, so this is theta, correct? Then this is for the theta prime, this is for the theta double prime. Theta double prime will be something like that, and for this GP zone So as you clearly see here, if I heat the sample at about, say this is about 200, so 150 degrees Celsius number, this is 100, something like 100, this is 150. If I do that, first phase which will form is the GP zone, because I am increasing the time. So first it will hit here from the GP zone. Then if you heat it temperature, if you increase the time more, slowly these phases will start appearing. As you see here, these phases are connected, these diagrams are connected, so slowly theta double prime, theta prime, and finally theta will appear for longer time duration. So depending on our use, depending on our need, we can actually stop the heat treatment anytime. Okay, as very clear that we can never have a single precipitate at any time, except at a very high temperature, very high time, when theta will completely form out of the sequence. But if I stop here, we will have a mixture of theta prime, double prime and GP zones. If I stop there, you will have a mixture of GP zones plus theta double prime and theta. If I stop there, you will have a mixture of GP zones, theta double prime, theta prime, and little bit of theta. So simply by doing our heat treatment cycle, that is by simply adopting temperature and time properly, basically temperature don't change much, the time, we can actually have combinations of different mixtures of the phases in the microstructures. And by doing so, we can actually create different mechanical properties. We can actually get different mechanical properties, create different microstructures and get that. That is what is the major advantage of these alloys, aluminum copper alloys. You can actually do lot of different types of heat treatments and to improve their properties or to get different combinations of the mechanical properties, possible to do that. So simply by these things are available normally to the people who are working in the industry, these diagrams, and they can actually choose, they will have values written here also, they can actually choose the time scale required at different temperatures, 100 or 150, and get the precipitates and phases combinations differently depending on the need. So obviously, as you have seen, only getting GP zones will not give you the best properties. You must have a combinations of theta double prime and GP zones in the microstructure. So depending on your need, you can actually choose different heat treatment cycles. This is very important in the sequence. Remember, this is an eutectic alloy. That's another important aspect I should discuss. This is an eutectic alloy. Normally this is about 33% of weight percent of copper with about 67% of the aluminum provides you eutectic between alpha and the theta. Okay. So all these alloys, although it looks like that if I have about 4 to 4.5% copper alloys, small amount of eutectic is present in these alloys. It's very difficult to stop that, because when they are actually continually solidified from the liquid, this although it looks like that this will have a single alpha phase, but because of the coring, in during the continuous solidification, there will be always some liquid left over at the end, and this liquid, as the copper is rejected into liquid, this liquid will have a very high copper concentrations, and that is one of the problem in these alloys. Because of that, some eutectic will be inevitably present, and this eutectics many cases actually creates in heat treatment, because although heat treatment temperature is very low, eutectic will not get affected, but the presence of the eutectic will hamper the mechanical properties. And that is why one has to be very clear about choosing the alloy compositions. One should not choose an alloy composition which is very close to this point. This is about 5.5% of the copper. So that is the reason actually 4 is optimally suited copper concentration in this alloy. And that is what I have been discussing with you for the last 1 hour. So it is very clear that by simply by simply looking at these precipitates, one can do that. And this book has real descriptions of these microstructures, nicely done, and you can actually look at it. In fact, it is possible to see this microstructure nicely in these books, which is required for you to understand how these precipitates form. Remember, this precipitate is actually very small size, and they can only be viewed under transmission electron microscope. And not only that, because of the crystallographic nature which I discussed with you last lecture, they must be seen under electron microscope. So that is actually about these precipitates, and remember there are other precipitates as I shown you, like in the first few slides, like aluminum, copper, magnesium, or aluminum, silver also I have shown you sometime, right, the aluminum silver here. So we will discuss some part of aluminum silver alloys in the next lecture, which is and then wind it up this particular chapter. But you know, this sequence of precipitation which I have shown you sometimes gets affected by the size of the precipitates. If you are actually keeping the sample at a certain temperature for a long time, let us suppose you keep it, then some of the precipitates will go bigger, and once they become bigger, they will again develop the size dependent incoherency in the interface, and that spoils the property. So therefore, size control is also very important in these alloys. Okay, let us stop here. So once we will discuss a bit about the aluminum silver alloys, which is also a classical system but never used because of the cost, because silver is very expensive compared to copper, but it is a very classical system in which less sequence is present. You have only GP zones and gamma prime, that is all. And then gamma is the equilibrium phase, which is nothing but Al to Ag to Al. It's same as like CuAl2, but it has different structure, not the same as these structures. We will discuss about that.